Hi, how are you? Today we start one of the topics related to fluid mechanics, general energy equation. We go through the following. We introduce the concept, energy losses and applications, and we define some of the terms for energy losses. And we talk about the general energy equations, how we calculate the power required by the pump, and the power delivered to the fluid motors. So from last year, if you download mechanics, you understand energy can be lost from a system through friction and valves and fittings. So we have edge losses in the system due to the friction and to minor losses. Also, energy can be added to the system by using a pump. Energy can be removed or lost from the system, for example, when you have turbines. And also, general energy equation is difference from Bernoulli's equations, as the Bernoulli's equation assumes there is no loss in the system, no energy loss in the system compared to general energy equation. So Bernoulli's is just an assumption that wherever is inlet to the system is the same will be outlet to the system. Also, you have learned the use of continuity equation, Q, which is the volume flow rate, meters cubic per second. Q1 is equals Q2. So whatever enters to the system should exist to the exit from the system with the same amount of volume flow rates. Q is calculated based on the cross-sectional area, pi over 4d square, units meter square, times the average velocity, meters per second. You multiply the units, the Q is measured in meters cubic per second. And this is very helpful. So when you have the Q and you have diameters, you can determine the velocities for at each point. Also, something you learned in the past from fluid mechanics, some of the terms, P over gamma is called the pressure head, Z is the elevation head, and V squared over 2G is the velocity head, could be calculated in Bernoulli's equation. So P1 over gamma plus Z1 plus V1 over V1 squared over 2G at certain point from the system equals P2 over gamma plus Z2 plus V2 squared over 2G. So that total term should be equal to that term. However, in general energy equation, that doesn't work. We'll go through that. So Bernoulli's equation has its own restrictions. For example, it's valid only for incompressible fluids. There can be no mechanical devices, so it's assumed there is no pump, no turbines between the two sections of interest, and also assumes there is no energy loss due to friction or the turbulence generated through the sudden enlargement or contraction or fittings such as elbows or even valves. And there can be no heat transfer into or out the fluid, so assume the no friction energy loss through the system. When no fluid flow system satisfies all of these requirements, so you need to take the requirements for the things we mentioned. Therefore, you need to use the general energy equation for real life fluids because it will take into account the energy transfers, which could be gain and losses through the system. This is an example from your textbook, Mott, which we have access to it. It's showing you the suction line is here, has a bigger diameter compared to the discharge line, entering to the pump, and from the pump going through the T, and there is a valve, and then goes to another valve, and then goes to an elbow 90 degree, and then go through a discharge line, which is long. So for this type of application, you find there is a gradual reducer to come from big diameter to small diameter section to enter to the pump. And then after that, you have a gradual enlargement to go back to it. So these are, we call them the fittings, minor fittings, the valve, the T, and the elbow. And those are lost from the system, causing me to lose. However, what is the gain from the system is the pump, which through the suction process taking the fluid from this point and then discharge it through the remaining point to go through it. So that is very important for us to understand what we're gaining, what we're losing from the system. But we need to define some of the terms. So energy is added to the system through a pump. Friction caused by the fluid traveling along the pipe also causes energy to be lost. In addition, at each valve, T, elbow, reducer, and enlarge, energy is lost from the fluid. So those are minor fittings. And we go through them one by one. But before that, we start with the pump. A pump is a common example of a mechanical device that adds energy to a fluid. Usually those pumps works by an electric motor or some other prime power device drives a rotating shaft in the pump. The pump then takes this kinetic energy and delivers into the fluid, resulting in a fluid flow and increased fluid pressure. You could have a gear pump similar to that one, suction and discharge line, or you could have a piston pump. You see the inlet and outlet, how they are located with respect to the schematic diagram. Fluid motors, such as turbines, rotary actuators, you're actually taking the energy after the pump is delivering to convert it to a mechanical, and then later you can transfer that energy. This is an energy loss from the system. So most fluid motors have the same basic configuration as pumps shown in the previous slides. However, the difference between a pump and a fluid motor is that when acting as a motor, the fluid drives the rotating elements of the device, whereas the reverse is true for pumps. Fluid due to friction. A fluid in motion offers frictional resistance to flow. Part of the energy in the system is converted to thermal energy, which is heat, and those are due to the internal walls of the pipe in which the fluid is passing or flowing through. The magnitude of energy loss is dependent on the properties of the fluid, the flow velocity, the pipe size, the smoothness of the pipe wall, and the length of the pipe. And this is related to using Moody chart. Moody chart is based on Reynolds number. Reynolds number is calculated by density times velocity times the diameter of the pipe divided by dynamic viscosity. So these are, in this equation, you have the following properties of the fluid at certain temperature, the diameter or the size, pipe size, and the velocity. And as well, you need the relative roughness for the pipe, whatever the pipe is made of. You intersect between Reynolds number and relative roughness, you find the friction factor. And then based on that, you can calculate the friction loss. So valves and fittings, elements that control the direction of flow or rate of fluid in a system, typically set up local turbulence in the fluid, causing energy to be dissipated as heat. That's type of heat, we call them minor losses. Change in the flow velocity or change in the direction of flow, these energy losses occurs because like in an elbow, you can see that in applied computational modeling, such as we done in CFD modeling. In a large systems, the magnitude of loss due to the valves and fittings is usually small compared with the friction loss, and that's why we call them minor losses. If we define some of the terms with respect to general energy equation, now we learn the following. HA is energy added to the fluid with a mechanical device, such as a pump. Also, we could call it total head on the pump. However, if we want to mention the energy removed from the fluid, such as if you have a turbine, we call it HR. And the energy loss from the system is due to friction in pipes and or minor losses. I'll put and here as well due to valves and fittings. So HL is the total energy losses from the system. HL for minor losses needs to be calculated using the following equation, which is K is the resisting coefficients multiplied by V squared over 2G. And it's recommended to do that for each section and discharge line separately. Now, if we go to the general energy equation, you can find it in the following example. I'm trying to calculate the general energy equation between point 1 and point 2. I have the following: pump, valve, elbow, and I have as well a motor. So if we mention what is going on here, we have a pump is a HA added to the system, and you have the valve minor losses, elbow minor losses, elbow minor losses, and you have the length of the pipe, which is the friction, and you have HR is the losses. So if we use only Bernoulli's equation, we used to write P1 over gamma plus Z1 over plus V1 squared over 2G equals P2 over gamma plus Z2 plus V2 squared over 2G. But with general energy equation would be that term I just mentioned plus HA added to the system minus HR removed from the system minus H losses to the system equals to that term. This is very important because such a system expression is starting from the principle of conservation of energy. That is the equation we need to be aware of. And this is how you write the general equation in terms of pressure and Z elevation and velocity head, and adding the following HA related to the pump, HR related to the turbine or motor, minus H losses. Now, if you say if in my example I don't have HR, then you remove it. You don't need to include that term. If you don't have a pump, the same thing. It's essential that the general energy equation be written in the direction of the flow. So P1 must be the direction for starting from the suction line going towards the discharge line. That is from the reference point on the left side of the equation to the on the right side. This is an example. You have a reservoir tank. Water flows from a large tank at the rate of 0.034 meters cubic per second. So this is the Q through a pipe system. Calculate the total amount of the energy loss from the system because of the valve, the elbow, the pipe entrance, and the fluid friction. If we try to see this example very carefully, we have a valve, we have elbow 1, elbow 2, we have the following length of the pipes. So 3.96, and this one is the elevation. So you could take that into account, the length of the pipe, or you may not take it, depends on the information given to us. So how can we solve this to find the total amount of energy loss from the system? So if we start from point 1 and 2, you can see that we have the diameter here, 7.6. We have the Q. So Q equals VA. Velocity equals Q divided by A. A is pi over 4 and the diameter square and Q. And then you find the velocity V2. V1, because the small tank, we assume velocity at the surface of the tank. We see the tank is vented. It's 0, and the pressure gauge when it's vented tank is also 0. There is no pressure there. So P1 V1 equals to 0. And then we go on through the points. The elevation between them, between point 1 and 2, is the addition of 3.66 plus 3.96. So that is the total elevation, or we could say delta Z, Z2 minus Z1. Right. Let's see how can we solve that. We write first the general energy equation, P1 Z1, P1 over gamma Z1 V1 squared over 2G, HA minus HR minus HL, P2 over gamma plus Z2 plus V2 squared over 2G. Look carefully here. We put everything into account, but now we see which one we don't need. P1 equals 0, as I say, is open to atmosphere, so P gauge is 0. P2 is also open to the atmosphere, its P gauge is 0. V1 approximately a surface area of reservoir is large, so we assume it's close to 0. HA and HR are not considered 0 because we don't have a motor, we don't have a pump. So what is remaining from this equation? Z1, Z2, or Z1 usually, Z1 that should be, and you have H losses, and Z2 and V squared 2 over 2G. So that is the remaining of the equation. Rearranging that, HL equals Z2 minus Z1. Z2 minus Z1, but we bring that positive, so it would be Z1 minus Z2 minus V squared over 2G. Z1 minus Z2 is the total of that, the total elevation, which is 7.62 when you add these two values. V2, as I mentioned, is Q over A, the area for 7.6 centimeters diameter. So V2 can be found from this equation to be equals 7.56 meters per second. V square 2 over 2G, it will be just using the following equation, 2.913. H losses, it's equals 7.62 minus 2.913, and that will give us 4.707, which close to 4.71. The answer in HL is 4.8. Some of them, they assume it. Here is how it's found, because Q was given and the area of 7.6 diameter was given to us, so we can find the velocity. Very simple. You write the general energy equation, and based on it, you can determine each one of them. Example 2. The volume flow rate through the pump is 0.014 meter cubic per second. The fluid being pumped is oil with a specific gravity of 0.86. Calculate the energy delivered by the pump to the oil per unit weight of oil flowing in the system. Energy losses in the system are caused by the check valve and friction losses as the fluid flows through the pipe. The magnitude of such losses has been determined to be 1.86 newtons meters per newton. I give you time just to read the question. Right, so information given to us. Q, specific gravity, wants us to find the energy delivered by the pump. So we have a pump in this example. The fluid is oil. That's why we're giving us specific gravity. Energy losses in the system are caused by the check valve. So we have a check valve and friction losses as the fluid flows through the pipe. The magnitude of these losses are 1.86, calculated similar to what we've done. So what they want us to do in this question, calculate the energy delivered by the pump. So once HA. We looked at the question. Don't worry about these dimensions. If you go to the textbook, you find the 3-inch schedule 40 steel pipes with the SI units for the diameter, and even you can find the cross-sectional area straight from the appendices from the textbook. You have point A, this is the direction of the flow, so we always start from A to go to B. A pressure here is given to us is a negative vacuum minus 28 kilopascal, going to gauge pressure here to 196 kilopascal at point B. This also got 2-inch schedule 40 steel pipe. Again, from appendices from textbook, you can find these values. And the direction of the flow. We write the general energy equation. We have H losses. We don't have motor. We have pressures. We need to determine the velocity. Since we have the volume flow rate, we have the diameters or areas, we can definitely find the velocity at A and velocity at B easily with no issues. So, general energy equation, PA over gamma, ZA, VA squared for 2G, plus HA minus H losses. H losses is 1.86, and you write the following parameters. Rearranging the equation, HA is equal PB minus PA, over gamma, delta Z, VB squared minus VA squared plus H losses. Gamma is the specific gravity for the oil, 0.86 times 1000 times 9.81, which is the density or specific weight for water at room temperature. The pressures are given to us, so you can easily, we add them. 296 minus 28, that would give us 38.4 after dividing that by gamma for oil. Z, if you look on it between them, between B and A, which is, it's given as one value. So if this is a reference point is 0, going up is 1 meter. So it's a positive number. Therefore, we can use the definition of continuity equation, Q equal AV. So AA VA equals AB VB. Based on that, you have the Q, and using Appendix Fs, as I mentioned, for the 3-inch and 2-inch Schedule 40 pipes, you can find these values for the cross-sectional areas to determine velocity at point A, 2.94 meters per second, and velocity at point B, 6.46 meters per second. Finally, you add these together, divide by 2G, you get 1.69. So now we converted everything to meters. So HA 38.4, that is from the pressure difference divided by specific weight, plus 1 meters, which is the elevation head, and 1.69, which is the velocity head. And then you have the H losses 1.86. Then you find the total head delivered or added energy added to the system by the pump is 42.9 meters, or we call it newtons times meters per newtons, which is that's how we mention them. Pump delivers 42.9 newton meters of energy to each newton of oil flowing through it. Remember, to each newton, so a newton by newton will be cancelled, so it's 42.9 meters. That is the pump's delivering it. And then you follow this question. Now, another things we need to determine is the power required by the pump. Power is defined as the rate of doing the work. In fluid mechanics, we can modify this statement and consider that power is the rate at which energy is being transferred. From SI units, the power is in watts, which is 1 newtons meters per second, or 1 joules per second, where joule is the J is the joules. Now that's an example 2. We found the pump was delivering 42.9 newtons per meters of energy to each newton of oil as is flowed through the pump. How would we calculate the power delivered to the oil? To do this, we need to determine the weight of the flow rate, W, which is in how many newtons of oil are flowing through the pump in any given amount of time, and has the units of newtons per second. So power for that equation equals HA times the weight. The weight is specific weight of the oil times the Q, which is the volume flow rate. Specific weight of the oil, which we calculated the specific gravity times 1000, density of water at room temperature times 9.81, and you have the Q, which is giving the question. So HA is already calculated. Gamma, it's 8.44. And Q 0.014 is given to us. You bring the equation together, the power required by the pump, you multiply these values, you get about 5.069 kilowatts power required by the pumps to operate the pump. Another terms we need to understand is the mechanical efficiency of the pump. The definition of efficiency is used to denote the ratio of the power delivered by the pump to the fluid to the power supply to the pump. Because of energy losses due to mechanical friction in pump components, fluid friction in the pump, and excessive fluid turbulence in the pump, not all of the input power is delivered to the fluid. Then using the symbols for mechanical efficiency, some of them in this textbooks write it EM, power delivered to the fluid, power put into pump. So PA divided PI. PA, we just calculated power required by the pump, divided by the power put into pump, and the value of EM will be always less than 1, like 100%. So we're trying to get point something, 0.6. Usually it's a good and acceptable efficiency. So the value of the mechanical efficiency of the pump depends not only on the design of the pump, but also on the conditions under which it's operating, particularly the total head and the flow rate. Efficiency values for positive displacement fluid power pumps are reported differently from those of centrifugal pumps. So that's why you need to be aware which pumps you're selecting. 3 values are often used: overall efficiency, or volumetric efficiency, and transitional efficiency. In general, the overall efficiency is analog to the mechanical efficiency. discuss for other types of pumps in this section. Volumetric efficiency is a measure of the actual delivery from the pump compared with the ideal delivery found from the displacement per revolution times the rotational speed of the pump. Torsional efficiency is a measure of the ratio of the ideal torque required to drive the pump against the pressure it's developing to the actual torque. And that's the end of this presentation. Hopefully you enjoy it. Please, if you have any questions, write in the comments. I can answer you and go through the next topic very soon.